Welcome to the Deep Dive, the show where we cut through the noise and get straight to the knowledge. Today we're unraveling a fundamental process that quietly shapes the materials all around us, often making them stronger, more resilient. Imagine a steel gear, maybe like one in a car transmission. Its outer layer, the case, is deliberately made harder than the inside, the core. But how? Well, it happens through a high-temperature heat treatment. Carbon atoms, literally from the atmosphere around it, move into the surface of the steel. This makes it tougher, more wear-resistant. And this whole thing hinges on a fundamental phenomenon: diffusion.
And that's exactly what we're diving into today. It isn't just about hardening gears. Diffusion is really a critical process. It underpins countless material treatments, countless technologies, from metallurgy, like you just said, to the tiny microelectronics powering our devices. So today we're exploring this essential concept from your material science studies. We'll uncover the mechanisms behind how atoms actually move, understand the principles governing how fast and how far they go, and look at the real-world implications. Our mission really is to give you a clear step-by-step understanding, so you walk away feeling genuinely informed, but, without getting lost in all the details.
Okay, let's unpack this. Diffusion. At its heart, it's simply material transport by atomic motion. Sounds fancy, but it just means atoms are constantly moving, even in solid materials. It's like a microscopic dance happening perpetually. And you can actually see the results of this if you set up what's called a diffusion couple. Picture taking two different metal bars, let's say copper and nickel, and clamping them together really tightly. Initially, you'd see a sharp, clear line right where the pure copper meets the pure nickel. Now, heat this couple up for a while, keep it below their melting points, and then cool it down. Something amazing happens. That sharp boundary is gone. Instead, you'll find this blended, alloyed region right in the middle. Copper atoms have wandered into the nickel side, and nickel atoms have moved into the copper. If you plotted the concentration across the bar, it wouldn't be a sudden step anymore. It would be a smooth curve, gradually changing from like 100% copper on one side down to 100% nickel on the other. It's a real atomic exchange creating this gradient.
Exactly. And that migration of atoms of one metal into another, that's what we call interdiffusion, or sometimes impurity diffusion. It's where you see that net movement from high concentration to low concentration. But interestingly, diffusion also happens in pure metals. Atoms of the same type swap places. That's self-diffusion. You can't see it by looking, of course, because the composition stays the same. But it's happening constantly. And understanding these diffusion rates, both types, is just crucial for engineers. It lets them predict how materials will behave during heat treatments. They can enhance properties deliberately, or sometimes slow down processes they don't want, things that might degrade the material.
Okay, so how do these atoms actually take these tiny steps? Atomically speaking, it's a stepwise hop from one lattice site to another. For an atom to actually make that jump, two key things have to happen. First, there has to be an empty spot right next to it for it to jump into. An adjacent site needs to be vacant. And second, the atom itself needs enough energy, mostly vibrational energy, enough energy to break its current bonds with neighbors and sort of squeeze through, distorting the lattice just a tiny bit as it moves. At any given temperature, only a small fraction of atoms actually has this much energy. But that fraction shoots up significantly as the temperature increases.
That's right. And we generally explain this atomic motion in metals using two main mechanisms. The first one is vacancy diffusion. So picture that regular crystal lattice, that ordered arrangement of atoms. Now remember, there are always some missing atoms, empty lattice sites. We call these vacancies. In vacancy diffusion, an atom on a normal site essentially just swaps places with an adjacent vacancy. The atom moves one way, and the vacancy effectively moves the other way. So this mechanism absolutely depends on having those vacancies present, and their numbers increase a lot at higher temperatures. More vacancies mean more chances for atoms to jump.
Okay, so that's one way. What's the other?
The second mechanism is interstitial diffusion. Now, this is for very small impurity atoms. Think tiny things like hydrogen, carbon, nitrogen, maybe oxygen. These atoms are small enough to fit into the gaps, the little interstitial positions between the larger host atoms in the main lattice. So these small interstitial atoms just jump from one gap to a neighboring empty gap. The key here is size. Larger atoms, whether they're host atoms or other impurities substituting for host atoms, they just don't diffuse this way. They're too big to fit in the gaps. And what really stands out is that interstitial diffusion is usually much, much faster than vacancy diffusion.
Master, why is that?
Well, two main reasons. The atoms doing the jumping are smaller and just more mobile. And crucially, there are generally way more empty interstitial positions available for them to jump into compared to the number of vacancies, so more pathways open.
Right, that makes sense. So diffusion clearly happens over time, but how do we talk about how fast it happens? That's where we introduce the concept of diffusion flux, usually represented by J. Think of flux as basically the rate of mass transfer. It's the amount of stuff, mass, or atoms moving through a specific area per unit of time. The units are typically something like kilograms per square meter per second, or maybe atoms per square meter per second. It's quantifying that flow.
Precisely. And sometimes this flow, this diffusion flux, stays constant over time. Imagine a situation where the amount of stuff diffusing into a material is exactly balanced by the amount leaving it, no net buildup. When that happens, we call it steady-state diffusion. And the driving force behind the steady flow is the concentration gradient, how concentration changes with distance. And this leads us straight to a really fundamental principle, Fick's first law. Fick's first law basically says that this diffusion flux, J, is proportional to the concentration gradient, dc dx. J equals minus d times dc dx. That d is the diffusion coefficient. It's a measure of how quickly atoms diffuse, units of meters squared per second. And that minus sign is important. It just tells us that diffusion happens down the concentration gradient, from high concentration to low concentration, always.
Okay, so high concentration pushes atoms towards low concentration.
Exactly. And to visualize steady state, think of that thin metal plate again.
Yeah.
High pressure gas on one side, low pressure on the other. Gas diffuses through. If you could plot the gas concentration inside the plate versus position, you'd get a straight line, a linear profile. The slope of that line is the concentration gradient, dc dx, or, delta C over delta X for a straight line. A real-world example, purifying hydrogen. You can diffuse it through a palladium sheet. Palladium lets hydrogen through, but blocks other gases. That's steady-state diffusion at work.
That's amazing, the precision. So if you were looking at, say, carbon diffusing through an iron plate at 700 Celsius, and you knew the carbon concentrations at two different points, maybe 5 millimeters and 10 millimeter deep, and you knew the diffusion coefficient D, you could actually use Fick's first law to calculate the exact flux, right?
Absolutely.
Like if the concentrations were 1.2 and zero point 0.8 kilograms per cubic meter at those depths, and D was 3 times 10 meters squared per second, the flux comes out to 2.4 times 10 kilograms per square meter per second. It tells you even tiny differences drive a measurable flow. Critical stuff for design.
It really is. But, most real-world diffusion isn't quite that simple. It's not steady state. More often, the diffusion flux and the concentration gradient at any given point in the solid, they actually change over time. This means you get a net buildup or maybe a depletion of the diffusing stuff in certain regions. This dynamic situation is non-steady state diffusion.
Right, things are changing. So that concentration profile wouldn't be a straight line anymore, or at least not stay the same line. If you plotted concentration versus distance at different times, like after 1 hour, then 2 hours, then maybe 3 hours, you'd see the curve changing shape, right? You would probably flatten out and stretch deeper into the material as time went on, showing the atoms moving further in and spreading out.
Exactly. And for these dynamic, time-dependent cases, we need Fick's second law. It's a bit more complex, a partial differential equation, but assuming the diffusion coefficient D is constant, it simplifies nicely. Basically, it describes how concentration changes with both position and time. It's the mathematical tool for tracking these evolving profiles, and there's a very useful, very practical solution to Fick's second law for a specific scenario. Imagine a semi-infinite solid, basically. The material is thick enough that the diffusing atoms don't reach the other side during the process. And you hold the concentration right at the surface constant. This happens all the time in treatments like carburizing.
Ah, like hardening the surface of that steel gear we started with.
Precisely. You're diffusing carbon into the steel from a gas, keeping the surface carbon level constant. The solution for this involves a mathematical function called the Gaussian error function, often abbreviated ERF. The equation looks like CFC0, CSC0, often ERF by 2C rati. Let's break that down. CS is the concentration you get at a depth x after time t. C0 is the initial concentration everywhere in the material. CS is that constant surface concentration. And D is the diffusion coefficient. The error function part, ES0, where Z is by 2EC, well, its values are tabulated. You just look them up. If you plotted this equation, you'd see a curve starting at CS right at the surface, and then dropping off towards C0 as you go deeper, X increases. The shape depends on that error function.
Okay, that sounds really powerful for controlling treatments. Let's try an example. Say you want to harden that steel gear. It starts at 0.25 weight percent carbon, C0. You heat it to 950 degrees C. You keep the surface concentration constant at 1.2 L weight percent carbon, CS. How long does it take to reach 0.80 weight percent carbon, CX, at a depth of 0.5 millimeters? You'd plug in CX, C0, C's and X. You also need the diffusion coefficient D at 950 degrees C, which is known, say, 1.6 by 10 euro FDZ. Then you rearrange the equation to find the value of the error function.
Right. You calculate CXC0, CSC0, then find 1 minus that value. That equals error FC. You look up that earth value in the table to find the corresponding z. CZ will fit into 30D, and you know x and d, you can solve for t.
And the calculation shows it takes about 25,400 seconds, which is, what, about 7.1 hours?
Exactly. Real-world process times.
And there's also a handy relationship, right? Something like x squared over dt is constant.
Yeah, that's useful. If you want to achieve the same concentration, Cx, at the same depth, x, then the quantity x ddt must be constant. This means if you change the temperature, which changes d, you can easily calculate the new time pot needed.
Like comparing treatments. The example showed a 10-hour treatment at 600 degrees C for copper and aluminum is equivalent to over 110 hours at just 500 degrees C. That temperature difference really matters.
It makes a huge difference. Which brings us nicely to the factors that actually influence diffusion speed, that diffusion coefficient d. It's not fixed. It depends heavily on several things. Think of it as controlling the difficulty of that atomic road trip. First off, the diffusing species and the host material themselves are critical. For instance, carbon atoms diffusing in standard alpha iron move much faster than iron atoms moving in that same alpha iron. That's interdiffusion versus self-diffusion.
Like such much faster.
It goes back to the mechanism. Carbon uses that fast interstitial path, squeezing between the iron atoms. Iron atoms have to use the slower vacancy mechanism, waiting for an empty spot.
Ah, right. The smaller interstitial atoms have an easier time.
Definitely. Second, and this is maybe the biggest factor, temperature. Even a modest increase in temperature can cause a huge jump in the diffusion coefficient. Think about this. For iron self-diffusion in alpha iron, going from 500 degrees C to 900 degrees C increases D by about 6 orders of magnitude.
6 orders. That's a million times faster.
A million times. It's dramatic. Why? Because at higher temperatures, way more atoms have enough vibrational energy to actually make those jumps. And this temperature dependence follows a specific mathematical relationship, an exponential one. dE0 xp, qd RT. Let's unpack that. D0 is a constant independent of temperature. QD is the activation energy for diffusion, R is the gas constant, and T is the absolute temperature in Kelvin. You can think of Q, that activation energy, as the energy barrier that 1 mole of atoms needs to overcome to diffuse. Higher Q'd means slower diffusion. It's harder to make the jump.
An exponential relationship. That explains the millionfold increase.
It does, and if you take the natural logarithm of both sides of that equation, you get something linear. ln d0 qdr 1t, or using log base 10, log d0 qd 2.3r 1t. This is incredibly useful because it means if you plot the logarithm of the diffusion coefficient log d on the y-axis against the reciprocal of absolute temperature 1t on the x-axis, you should get a straight line.
Okay, a straight line plot. How does that help?
Well, if you look at such a plot, which often shows data for several different metal diffusion systems, you'll see these straight lines. The slope of each line is directly related to the activation energy, Dennis UD 2.3R, so you can determine QD from the slope. And the y-intercept, where the line crosses the y-axis, if you extrapolate it back to 1t, x00, gives you log D0. This is how we experimentally find those D0 and QD values that you find listed in tables for various systems, interstitial, self-diffusion, interdiffusion.
Got it. So it connects experiments to the theory.
Mm-hmm.
And you can use those values. If you need D for, say, magnesium diffusing in aluminum at 550 degrees C, you just look up D0 and QD for that specific pair in a table, plug them into the D0 XB QD or T equation, with T equals 550 plus 273 Kelvin.
And you calculate D directly. For that case, it comes out around 6.7 by 10 euros.
You can work backwards too, right? Use a plot to find the constants.
Absolutely. If you have experimental data plotted as log D versus 1T, like for copper diffusing in gold, you can pick 2 points on the line, read their log D and 1T values. Then you can calculate the slope to find Q'd, and use one of the points and the calculated 2D to solve for D0.
The source material calculated QD is 194 kilojmol, and D0 is 5.2 x in euro MUS for that copper and gold system.
Exactly. And this knowledge is what allows engineers to precisely design heat treatments. Going back to that steel gear one last time, if you need a specific carbon concentration at a certain depth for proper hardening, you can use these equations and constants to figure out the required time at different temperatures. Maybe it's 29.6 hours at 900 degrees C.
Or maybe just 5.3 hours if you crank the heat up to 1050 degrees C.
Right. You can trade off time and temperature to get the result you need, all based on controlling diffusion.
Okay, so we've gone from gears to the fundamentals. Now let's zoom way in to the nanoscale. How does diffusion play a role in semiconductors, in the chips in our electronics?
Oh, it's absolutely vital there. Making integrated circuits, or ICs, requires creating incredibly precise concentrations of impurity atoms, called dopants, within extremely tiny regions of silicon. And this is often achieved using a carefully controlled two-step diffusion process. First, there's pre-deposition. In this step, impurity atoms, maybe boron or phosphorus, usually from a gas source, diffuse into the silicon wafer. Crucially, the surface concentration Cs is kept constant during this phase. So we're back to using that error function solution to fix second law we talked about earlier.
Okay, so load the surface and let some diffuse in. What's next?
The second step is drive-in diffusion. This is done at a higher temperature, often in a different furnace atmosphere. The goal here isn't to add more impurities, but to push the impurities already introduced during pre-deposition deeper into the silicon. This creates the final desired concentration profile and junction depth. Often, an oxidizing atmosphere is used, which grows a thin layer of silicon dioxide on the surface.
Why the oxide layer?
It acts as a cap, a barrier. It prevents the dopant atoms from diffusing back out of the silicon during the high-temperature drive-in. Now, if you visualize the concentration profiles, drive-in looks different from pre-deposition. After pre-deposition, the concentration is highest right at the surface and drops off as you go deeper. But after drive-in, the total amount of impurity is fixed, no more coming in. So the peak concentration actually drops and moves inward away from the surface. The profile becomes broader and deeper.
Okay, so it pushes the peak concentration below the surface.
Exactly. And this also defines the junction depth, xj. That's the depth where the concentration of the diffusing impurity matches the background concentration of the silicon wafer itself. It marks the edge of the doped region. There are equations that describe this drive-in profile too, based on the total amount of impurity introduced during pre-deposition, which we call Q0.
It's really like atomic engineering, shaping these tiny regions. So, for example, diffusing boron into a silicon wafer. You do the pre-deposition step, calculate the total boron introduced, Q0. Then you do the drive-in step, use the drive-in time, temperature, which gives you D. And at Q0, you can calculate the final junction depth, xj. The example calculation showed xj could be around 2.19 micrometers.
Tiny. Extremely tiny. And you can also calculate the boron concentration at any specific depth within that profile, like 1 micrometer deep. Precision is key.
So after creating these dope regions through diffusion, you need to connect everything up on the chip, right? With tiny wires.
That's right. You deposit highly conductive circuit paths called interconnects. They carry the electrical current between transistors and other components. So here's a design question. Which metal should you use for these interconnects?
Well, common sense says you want the best conductor, right? So maybe silver or copper or gold. They have the highest electrical conductivities.
You'd think so. Looking at the numbers, silver and copper are definitely better conductors than, say, aluminum. Aluminum's conductivity is noticeably lower.
Okay, so why on earth would they often use aluminum? Seems like a compromise.
But here's where diffusion throws a wrench in the works and becomes the absolute deciding factor. After depositing these interconnects, the chip often goes through more heating steps, maybe up to 500 degrees C for other processing. Now, what happens if the metal atoms from your interconnect diffuse significantly into the silicon underneath during this heating?
Oh, that sounds bad. It would mess up those carefully doped silicon regions, wouldn't it?
Exactly. It would destroy the electrical properties of the transistors in the circuit. Game over. So the critical property for an interconnect material isn't just conductivity, it's having an extremely low diffusion coefficient in silicon at those processing temperatures. Now, if you look at a plot of log D versus 1T for various metals diffusing in silicon copper, gold, silver, and aluminum, at 500 degrees C, the difference is staggering. The diffusion coefficient for aluminum and silicon is incredibly small, about 3.6 by 10 on Equal test.
10 to the minus 26, that's vanishingly small.
It is, and it's at least 8 orders of magnitude. That's 100 million times lower than the diffusion coefficients for copper, gold, or silver in silicon at the same temperature.
Wow. So aluminum barely moves into the silicon at all, even when heated.
Precisely. And that is why aluminum was the workhorse for interconnects for decades, despite not being the best conductor. Its resistance to diffusion protected the underlying silicon. Sometimes alloys like aluminum copper silicon are used for even better performance or reliability.
What about now? I hear about copper interconnects more often these days.
That's true. Copper is used now for higher performance because of its better conductivity. But it requires a sophisticated barrier layer, often tantalum or tantalum nitride, placed between the copper and the silicon. This barrier layer's job is specifically to block the copper atoms from diffusing into the silicon. It adds complexity, but allows the use of copper.
So diffusion dictates material choice, even against other desirable properties. Fascinating. Okay, one last quick point. We've mostly talked about atoms moving through the main body, the bulk of the material. Are there other pathways?
Yes, briefly, it's worth mentioning that atoms can also migrate along what we call short-circuit diffusion paths. These include things like crystal defects called dislocations, the boundaries between different crystal grains, grain boundaries, and the external surfaces of the material.
And diffusion is faster along these paths.
Much faster generally. The atoms are less tightly packed along these defects or surfaces, so it's an easier route. However, in most practical situations involving bulk diffusion, the contribution from these short-circuit paths to the overall amount of material moved is usually pretty small.
Why is that, if they're faster?
Because the actual cross-sectional area of these paths, the total width of all grain boundaries and dislocations is tiny compared to the area of the bulk material. So while the rate is high, the volume of traffic is low.
Got it. Fast lanes, but very narrow ones.
A good analogy.
All right, let's recap this deep dive then. We've really journeyed into the atomic world today. You've seen that diffusion is this fundamental process of atoms moving within solids.
We explored the two main ways they do it. Vacancy diffusion, swapping with empty spots, and interstitial diffusion, where small atoms zip through the gaps, and that one's usually much faster.
We unpacked Fick's first law for steady-state situations where the flow rate, the flux, is constant and driven by the concentration gradient. Che Gills's -d dc dx.
And then Fick's second law for the more common non-steady state cases where concentrations change with both time and position. We saw its practical solution for things like carburizing steel using the error function to predict profiles.
And critically, we saw how much diffusion depends on the materials involved and especially on temperature. That exponential relationship, D equals D0 xp qdRT, and the importance of the activation energy, QD.
And you've seen the real-world impact from making steel gears tough
To the incredibly precise doping of semiconductors and even dictating the choice of metal for interconnects in computer chips, where low diffusion trumped high conductivity.
It really shows the power of understanding and controlling things at the atomic scale.
It's quite amazing, isn't it? Thinking about how these invisible, minuscule movements of atoms ultimately determine the strength, the function, the reliability of almost everything around us. From huge structures to tiny electronics. Makes you wonder, what other material behaviors are governed by these hidden atomic dances, just waiting for us to understand them? Well, thank you for joining us on this deep dive into diffusion. From all of us here on the Deep Dive team, we hope you feel more informed and maybe even a little inspired to keep exploring the fascinating material world.